Değerli katılımcılar, değerli dostlar, herkese iyi akşamlar. TÜBİTAK Temel Bilimler Araştırma Enstitüsü, temel bilimin çeşitli dallarında ve disiplinler arası alanlarda düzenlediği uluslararası seminerler serisiyle en üst düzey ve yenilikçi bilgileri ülkemizin ve dünyanın bilim ve eğitim camiasına aktarmaya devam etmektedir. Bu akşam yine bu vesileyle bir araya gelmiş bulunmaktayız ve ben de bu vesileyle hepinizi saygı ve sevgiyle selamlıyorum. Modern bilimin ortaya koyduğu en önemli keşiflerden biri fiziksel evrenin genişleme gerçeğidir. Alexander Freedman, Einstein genel relativite denklemlerinin ilgili çözümlerini inceleyerek evrenin genişleme gerçeğini teorik olarak öngören ilk bilim insanıdır. Ne yazık ki bu öngörüsünden kısa bir süre sonra dünyasını değişmiş ve yazdığı kısa bir makalesinin kosmolojide nasıl devrim yarattığını görememiştir. Edwin Hubble, evrenin genişleme gerçeğini deneysel olarak astronomik gözlemlerle keşfetmiş, genişleme yasasını ortaya koymuştur. Bu yasadaki evrenin genişleme hızının bir ölçeği olarak ortaya çıkan bir sabit veya parametre, günümüzde Hubble sabiti olarak bilinmektedir. Son zamanlarda bu sabitin farklı yöntemlerle belirlenen değerinin aynı olması gerekirken farklı olması, evren biliminde oldukça sıcak tartışmalara yol açmaktadır. Bu durum bazen fizikte yeni devrimsel bir açılımın habercisi olarak da algılanmaktadır. Bütün bunları bu akşam son derece değerli ve dünyaca ünlü bilim insanı Profesör Wendy Freedman'dan Chicago Üniversitesi ABD Hubble sabitine ilişkin gerilim bize neyi anlatır konuşmasından öğreneceğiz. Seminerimiz İngilizce olarak gerçekleştirilecektir. Bu nedenle İngilizce devam edeceğim. Dear Professor Wendy Freedman, dear participants, dear colleagues and friends, a very warm hello everyone and welcome. Welcome to the inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences. We organize these seminars for national and international audiences, relying on the unifying feature of science for humanity and with the participation of distinguished scientists and great speakers of the world. We also organize these seminars to mitigate the negative impacts of COVID-19 situation in the world on scientific thought and its creation. It is now my pleasure to inform you that this evening we have another wonderful episode of our Astronomy and Space Sciences seminar series. And I have a distinct pleasure and honor to introduce you our very special speaker, distinguished scientist, astronomer, and world-class expert in the field, Professor Wendy Laurel Freedman from the University of Chicago, United States. Professor Wendy Freedman has kindly agreed to join us for this seminar, and she's going to give a great talk. What is the tension in Hubble constant telling us? At the end of the talk, we will have a question-answer session, where questions can be asked by sending a message through the chat button of the Zoom platform or just by raising hand. Wendy Freedman is a Canadian-American astronomer, best known for her measurement of the Hubble constant. Annette John and Marianne Sullivan University Professor in Astronomy and Astrophysics at the University of Chicago. She received a PhD in Astronomy and Astrophysics at the University of Toronto. Joining the Carnegie Observatories in Pasadena, California, as a postdoctoral fellow, she became a faculty member of the scientific staff 3 years later. And as the first woman to join Carnegie's permanent staff. In 2003, she was named to the Crawford Greenwald Chair and Director of the Carnegie Observatories. Freedman was co-leader of an international team of 30 astronomers to carry out the Hubble Space Telescope key project. She also initiated the Giant Magellan Telescope project and served as chair of the board of directors from its inception in 2003 until 2015. Professor Freedman is a member of the National Academy of Sciences, a member of the American Academy of Arts and Sciences, a member of the American Philosophical Society, and a fellow of the American Physical Society. She has received the Magellanic Premium Award of the American Philosophical Society. In 1994, Freedman received Mark Aronson Lectureship and Prize in recognition of a decade of fundamental contributions to the area of the extragalactic distance scale and the stellar population of galaxies. She has also been awarded a Centennial Lectureship of the American Physical Society in 1999 and a Cosmos Club Award in 2000. She's a recipient of the 2009 Gruber Prize for Cosmology. In 2016, she received Daniela Heyman Prize for Astrophysics, awarded jointly by the American Institute of Physics and the American Astronomical Society. In 2020, Professor Freedman was elected a Legacy Fellow of the American Astronomical Society. With this, I want to invite Professor Wendy to the stage to begin his talk. Wendy, good morning, and we are very honored to have you with us. Please begin your talk.
Good morning. Good morning. I will share my screen again, make sure that, can you see it?
Yes.
Good. Okay. Thank you very much for this invitation. It's a pleasure for me and also an honor for me to be speaking with you today. And I'm sorry I can't be with you in person, but maybe someday in the future. And yeah. I really like that even during these times of COVID, we can have worldwide connections of scientists. And that's maybe a silver lining in the pandemic. Today, I will speak about a lot of progress in observational cosmology, also theoretical cosmology, that's taken place over the last few decades. And we began a century ago. We didn't know yet that the universe was expanding with the discovery by Edwin Hubble in 1929 that the universe is expanding, and development of the general theory of relativity by Albert Einstein in 1915, there emerged a picture of an expanding universe that began with a Big Bang. And since that time, our technology has improved quite considerably, although there was a debate about the rate of expansion of the universe. Until a couple of decades ago, we were still debating at a level of a factor of 2. We didn't know whether the universe was 10 billion years old or 20 billion years old. And with the launch of the Hubble Space Telescope, we were able to refine those measurements and resolve that factor of 2 debate. Now, there has recently arisen a new tension that has come about as a result of very, very precise measurements of fluctuations in the temperature and also the polarization of the cosmic microwave background radiation. And those have tended to give a lower value of the Hubble constant than the values that we measure using a particular kind of star called the Cepheid variable star. And it's the same kind of star used by Edwin Hubble when he first made his discovery of the expansion in 1929. So if we look back in what we knew in cosmology in the 1980s, at that point, the cosmic microwave background had been discovered, the background radiation in 1965, and gave confirmation to the picture of a Big Bang universe. The theory of inflation was developed in the early 1980s by Alan Guth that posited a very rapid expansion early in the universe that led to the homogeneity and isotropy of the radiation of the background that we see today. And this famous cosmological constant, this is the constant that was suggested by Albert Einstein when he didn't have any evidence at that time that the universe was expanding. And he knew that it either had to be expanding or contracting. It couldn't be static. So he added this term lambda to force the universe to be static, and then later regretted it when Edwin Hubble discovered the expansion. And so in the 1980s, most astronomers and physicists assumed that the cosmological constant was in fact zero. And we didn't know whether or not, in fact, the matter density had not been measured to sufficient precision to determine whether we lived in an open universe that would expand forever, or whether, as people suggested at the time, that we lived in a critical matter density universe. That is a density that would either, if you exceeded it, the universe would collapse back upon itself. And if it was less than that critical density, it would expand forever. So those were the questions that were open at the time. And as I mentioned, we were arguing about the Hubble constant at a level of a factor of 2. And at that time, the range was 50 to 100 kilometers per second per megaparsec. Today, our picture of cosmology has emerged into what we now refer to as the standard cosmological model, the inflationary Big Bang universe, where 1/6 of the matter is in the form of baryons, which includes electrons and protons in this nomenclature. That is the ordinary matter out of which we are made, and planets and galaxies and stars. Whereas 1/3 of the universe is in total energy density, matter energy density of the universe is in the form of matter, most of which is dark matter. That is, it interacts gravitationally, but does not emit light. And 2/3 of the universe is in this form of dark energy, or perhaps the cosmological constant as suggested by originally Albert Einstein. We're arguing about a much smaller range in the Hubble constant right now, between 67 and 73 kilometers per second per megaparsec. So it's a considerable improvement in the accuracy with which we can measure the distances to nearby galaxies. And as I mentioned, now infer the expansion rate from measurements of the cosmic microwave background. Here is the change in the Hubble constant measurements that have been made from the early time. Hubble measured, in fact, a value of the Hubble constant that was about 500 kilometers per second per megaparsec. That came down when Walter Baade recognized that there were 2 different kinds of Cepheid variables, and the wrong kind had been used to calibrate the extragalactic distance scale. And then the field settled into this factor of 2 debate for a few decades, until the time of the key project, when we were able to get above the Earth's atmosphere, measure Cepheids in a larger sample of galaxies, use digital detectors, and resolve this factor of 2 debate, which we did in 2001. So just pictorially and simplistically, the current tension that we're referring to in the Hubble constant is that between what is inferred from measurements of the cosmic microwave background. And I'll mention that the values that are coming from the microwave background assume a cosmological model. So the standard cosmological model with a lambda term, 2/3 of dark energy in the model, and 1/3 matter. And allowing for that model, which I'll show you in a moment, is an exquisite fit to the data. You can infer the expansion today. That gives a value of 67. Whereas the Cepheid variables are giving something like 73 or 74. And the tension that has been quoted between those 2 values, of course, depends on the uncertainties that are adopted for those measurements. And it ranges between 3 to 6 sigma. Now, in physics, 5 sigma indicates a measurement that is essentially beyond doubt. It has overcome any kind of systematics, and it becomes a measurement that is well tested. very well tested. In astronomy and astrophysics, it's not unusual for 2 or 3 sigma tensions to disappear because of the kinds of systematic errors that are very difficult to overcome in astronomical observations. Now, I'm showing here the results of the Hubble constant that have been based on the calibration using Cepheid variables. Beginning now with our measurements with the Hubble Key project in the early 2000s, where we got a value of 72 kilometers per second per megaparsec with an uncertainty for the first time of 10%. Now, the value of the Hubble constant has remained very steady over time based on the Cepheid variables and tying in primarily to brighter objects, the type Ia supernovae. Most of the values that are shown here from a group that have themselves shoes. This is a Hubble program measurement over here, and we recalibrated the key project results using the Spitzer Space Telescope, which is sensitive to mid-infrared radiation, where the effects, for example, of scattering by dust grains is much smaller at longer wavelengths than it is in the visible, which Hubble primarily is sensitive to. Now, at the same scale here are the measurements of the cosmic microwave background. This is beginning here with measurements by the Wilkinson microwave anisotropy probe. And in the early 2000s, again, their first measurements indicated very good agreement with what we had obtained with the Key project. But with time, the measurements have come down, and these are measurements by the Planck satellite, European satellite. And you notice how the error bars have shrunk really quite significantly. This is a recent measurement by the Atacama Cosmology Telescope. And those are giving the lower values in the high 60s. Now, the most recent measurements, as we can see, the error bars, published error bars, don't even overlap. And that's what's given rise to this 3, 4, 5 sigma tension that people have been quoting. And so if this tension is real, that is, if there are not systematic errors that have not yet been uncovered, we don't know of any that at this point that would give rise to this difference. But if there are unknown systematics, then of course that tension would be much reduced. And that is something that I think we need to ensure that we have tested these results sufficiently. Extraordinary results, as the late Carl Sagan would say, require extraordinary evidence. And these are difficult measurements to make. Now, our group decided, because of this controversy, that it was important to obtain measurements of the Hubble constant that were completely independent of the Cepheid distance scale. So we had worked on Cepheids for many years. We knew where some of the difficulties were. And during the time of the Key project was designed to use 5 different methods to measure the Hubble constant. The samples were chosen so that the statistical uncertainties, they were large enough so that the statistical uncertainties were at a 5% level. The results were then combined to give a robust overall estimate of the systematic uncertainties. And nothing at the point of the Planck observations at that point had tested the Cepheids to that same new level of higher accuracy. So we began a new program with the Hubble Space Telescope to measure distances to galaxies using red giant branch stars. So this method, TRGB, stands for the tip of the red giant branch. These are the luminous giants in galaxies. And to then move out to calibrate the type Ia supernovae, as we do with the Cepheids, and independently determine the Hubble constant. I think our expectation at the time was that we would either agree with the cosmic microwave background results or the Cepheids, but in the end, we ended up in the middle. And that's where we are at the current time. This is a blow up now of the Hubble constant measurements that were in the 1970s, 1980s, showing you the scatter in the published values of the Hubble constant at that time. So they're scattering between 50 and 100. And this is the range now between 67 and 73 or 4 that we're now looking at. And so the question is, have we resolved the systematics? Eventually, this was resolved, the factor of 2 debate, and the now is, have we resolved the systematics to the point where we are learning something new and fundamental of the early universe? The recent measurements of the microwave background, I'm showing here results from the Planck satellite. This was their final measurement published in 2018. So it's now possible to measure these fluctuations in the temperature and also here at the bottom of the polarization to exquisite precision. So this is a thousandth of a percent precision now in these measurements. And shown is a fit. This is a 6-parameter fit now, this Lambda Cold Dark Matter model. The Hubble constant is not one of the 6 parameters. It's inferred given this cold dark matter lambda model. You can then infer what the expansion rate today is, and that's what leads to the 67. But you can see what a remarkable fit it is, how many peaks now in this acoustic oscillation spectrum are being measured, and so there's no evidence from the cosmic microwave background for a high value of the Hubble constant. It's completely consistent with this lambda CDM model. And here are the recent results from ACT, the Atacama Cosmology Telescope in Chile. There are also results from the South Pole Telescope, the SPT. And again, remarkable agreement between Planck and ACT. And this is an important test of systematics in the Planck experiment because these observations were made in Chile and completely independent instrumentation, frequencies, and so on. So from that end, there's an end-to-end test of the CMB measurements. So why is the Hubble constant, the Hubble tension interesting? And given that this current model, the standard cold dark matter model, has been so successful, it not only for the cosmic microwave background, but on all scales where we measured fluctuations in the matter density, the Lambda CDM model fits very, very well. Again, if you infer the Hubble constant, you get an accuracy of better than 1%. So the microwave background observations are setting the bar very high. We have not yet been able to achieve sub-percent precision in the local distance scale. That is beyond our means right now. And so if we make this comparison, we have to be, again, have tested for systematics at this level if we are going to infer this unambiguously. It's important to say, though, that with the current time, we have no understanding, physical understanding. What is the dark matter? What is the dark matter or the dark energy? What is the physical reason for the dark energy? What is the inflaton that's powering inflation? And so it's clearly critical that we test this standard model. And one of the best ways to test the standard model is to measure directly what the expansion rate is today and compare it to what you infer at high redshift, a redshift of 1100, the surface of last scattering for the cosmic microwave background, and see if those agree. And this would be a hint that there may be new physics if they don't agree. So let's say for the moment then, let's put aside any concerns about potential systematic errors and what could explain this difference between the high redshift, the early universe observations, and those that we're measuring today locally. And there have been many suggestions that have been made. In fact, they're approaching 1,000 papers that have been published on this topic about what could explain the tension that we're seeing. So I'm just going to go through these quickly. One possibility is that there's an additional neutrino. People talked about a sterile neutrino and some kind of relativistic species. And the difficulty now is, as I've shown you, the fit to these acoustic oscillation, the spectrum from the microwave background is so good now that you can't add something like an extra neutrino without having an effect on the peaks that are being measured. So you can't simply allow for a Hubble constant that's higher without having a tremendous effect elsewhere. People have looked for, so it's possible that there's some explanation, it could be some part of it, but you can't get to a Hubble constant of 73 or 74. Likewise, if you change the equation of state for dark energy from, that is the ratio of the pressure to the energy density for Einstein's cosmological constant, that's a value of W, this ratio of -1. So you could say maybe that changes as a function of redshift, but there are now very stringent constraints on how the Hubble parameter changes with redshift. And that you can't easily do anymore without running into other constraints. And similarly for dark matter particles that are decaying, modifying gravity, changing the spatial curvature, allowing for fluctuations that are non-Gaussian, a lot of attention to perhaps a scalar field before recombination that changes the expansion rate, but then disappears before it would have an effect on the observed peaks. And so what I should say is that at this time, there's no model that can satisfactorily explain a high value of the Hubble constant. You might get to 70 or 71, but not 73 or 74. It's very difficult to do. And there are also some indications that the fluctuations of the matter density, this sigma 8 parameter, that also is in tension with the microwave background. And trying to fit those both simultaneously doesn't work. So there's no one solution that would fit both of those issues. It's unlike the situation a couple of decades ago where the Hubble constant was in tension, the issue of whether we lived in an open universe or not, or a critical matter density universe, the large scale structure of the universe. All of that was resolved with the discovery of the acceleration of the universe and the dark energy in one go, as it were. And it solved a lot of problems that had existed. Right now, there's no solution to this. I'm just going to make quickly the point that we really need to be talking about accuracy of measurements. This decade has been termed precision cosmology, the time of precision cosmology. But of course, we don't want precision. We want precision and accuracy. And if we're off the target, it doesn't matter how precise our observations are. And it really is about systematics and convincing ourselves that we have overcome systematics as we had to do in the past. Very quickly, essentially how we build up the distance scale is to measure distances nearby using geometrical techniques, either nearby stars, measuring their parallaxes, which is becoming more and more accurate. There are also methods that make use of a supermassive black hole in the center of a galaxy and measuring the rotation about the black hole that allows you to measure a geometric distance. Then we step out into the realm of the Hubble Space Telescope, where we can measure Cepheid variables or these tip of the red giant branch stars in galaxies that have had type 1a supernovae. The type 1a supernovae are much brighter, so we can go to much greater distances. And we need to do that because, of course, galaxies interact gravitationally, they induce proper peculiar motions and perturb the Hubble flow. And so we need to get out to large enough distances where the expansion velocity is sufficiently large that these perturbations by nearby galaxies are not a significant fraction of the Hubble flow. And we do that by moving out to objects that have type 1a supernovae, where we can go out to the hundreds of megaparsec scales. The Hubble Space Telescope has been instrumental in allowing us to improve the distances to galaxies, getting above the Earth's atmosphere, where we can measure these stars are located in regions of gas and dust where they formed. They're young stars. We have to measure them against the background of the galaxy in which they're located. And so the Hubble let us get above the turbulence to measure very precise luminosities that are not crowded and blended by the locations of other stars that are nearby. So that made a huge difference in allowing us to overcome the factor of 2 uncertainty. These are the final results that we got from the key project. This is a plot of velocity as a function of distance, as Edwin Hubble originally plotted, although his data fit in this first tick mark here. We can now go to much greater distances using the type 1a supernovae, for example. I'm pointing out here that these are the residuals about the fit, and the objects that we can only measure nearby. You can see the scatter is larger because of these peculiar motions. This black line indicates a velocity of 5,000 kilometers per second. This is why we have primarily recently tended to use the type Ia supernovae because not only is the dispersion smaller, but they can be measured to larger and larger distances. So we obtained a value of 72 shown here, and I'm just showing the limits of other measurements that have been made recently, the Maser technique, surface brightness fluctuations, and these neutron star binaries, a so-called gravitational wave siren technique. So far, those methods don't allow us to go out nearly to the distances of the type Ia supernovae. And this is the value that we got, the statistical and the systematic uncertainties remaining at the time of the key project, and the 5 different methods that we used. More recently, we used the Spitzer infrared telescope to observe Cepheids at 3.6 microns. As I mentioned, longer wavelengths, you're less susceptible to the effects of dust. In fact, at 3.6 microns, the effect of dust is 17 times smaller than it is in the visual band, which we use with HST. And this is the period luminosity relation at 3.6 microns, so luminosity increasing up, period to the right. The scatter in this relation is only 1/10 of a magnitude, which translates to 5% in distance for a single star. And these are stars now observed. The labeled ones here are from our own Milky Way galaxy, for which at the time, 2012, we had parallaxes measured using the Hubble Space Telescope, the fine guidance system. And these are Cepheids in the Large Magellanic Cloud, which is a nearby irregular galaxy and has been used historically as the anchor to measure more distant galaxies relative to. Now, if you have a sample of 100, as in this case, then that means the statistical uncertainties are at the 0.5% level. And if you had no systematics, then you would have a Hubble constant at that level, but it is systematics that prevent you from getting that statistical uncertainty alone. And when we recalibrate the key project data, we obtain a Cepheid value of 74. So that's holding up for the Cepheids. I'll just mention that there's been a recent measurement to the Large Magellanic Cloud using a geometric technique, detached eclipsing binaries, and the agreement is excellent. It's at the 1% level, to a test of the key project results. Also, recent progress, enormous amount of progress in increasing the numbers of galaxies with Cepheid distances that can act as type Ia supernova calibrators. This is undertaken by the Shoes team, and they've measured Cepheids in 19 galaxies. You can see that the scatter goes up in distance. This is the Milky Way, and here's the Large Magellanic Cloud. But when you go out to Messier 101, it's only at a distance of 7 megaparsecs. That's relatively nearby. And NGC 4258, which is a galaxy that has these megamasers, the scatter already is up by a factor of 4. So we're pushing the limitations of the Hubble Space Telescope, even though the resolution is greater. It's fixed resolution for even, and as you go out to farther and farther distances, the crowding and blending of stars becomes more serious and the scatter goes up. Cepheid measurements to see, and just mention that one of these is the effect to which the luminosity of a Cepheid depends on the abundance in the metals in the atmosphere of the Cepheid. And this is something that we've been working on for 30 years. It's very difficult to pin down the value of this gamma coefficient very accurately. And also, as I mentioned, the image resolution, all of these are going to be improved with the launch of the James Webb Space Telescope, which is due to be launched December the 18th. So we're literally weeks away from now. So we're very excited about this and the opportunity to improve these measurements. Now, the tip of the red giant branch isn't as well known as Cepheids. Cepheids are the textbook classic example of how you measure the distances to nearby galaxies. But it has been used, in fact, also for a century. It was used by Harlow Shapley to measure the distances of globular clusters in the Milky Way galaxy. His scale was also wrong, as was Hubble's, but the technique has been around for a while. why do they make good distance indicators? And in fact, they are true standard candles, more so than the Cepheids or supernovae, which vary with time. And these are stars that have exhausted the hydrogen in their central cores. They have collapsed to the point where they have a helium core that is degenerate and a hydrogen burning shell surrounding the degenerate core. And the luminosity is being powered by the hydrogen burning in the shell. And the star increases in its luminosity. It's putting mass onto the degenerate core. The temperature is increasing until it increases to about 100 million degrees. At that point, stable helium burning can occur. That is a triple alpha process. And the star, because it can't expand its degenerate core, a thermal runaway occurs, and then the star begins to burn helium stably in its core, settles down onto the horizontal branch. But because of the degeneracy, this helium ignition occurs then almost at a constant core mass, and therefore at a predictable luminosity, which is what makes it such a good standard candle. And when we look observationally, so this is the Hertzsprung-Russell diagram, luminosity as a function of temperature, actually temperature to the left. And we look at, this is a nearby galaxy in the local group, at individual stars in the halo of this galaxy. We see stars on the horizontal branch where the stars come after they've undergone the helium flash. Here's the red giant branch. And this is the position at which the core helium flash occurs. And so even by eye, you can see that there's an edge to this a truncation. There are other stars, asymptotic giant branch stars, that are above the tip, but the contrast is such that we can still measure. Here in gray is shown the luminosity function. We measure the first derivative of that luminosity function. It's an edge detection technique that allows us to measure this peak very accurately, the position of the tip of the red giant branch. And of course, what we do is we add in artificial stars where we know the luminosities and the temperatures or colors of these stars, and we model the observed red giant branch, put them into our frames, and literally do this millions of times, extract them very repeatable and an excellent standard candle. This is something that we had started to look into in the early 1990s, where it became clear that if we observed in the I band filter, this is a filter at about 8,000 angstroms or 800 nanometers, that from models rich, the position of the luminosity, that is, of these stars, has very little dependence on the metal abundance, and also very insensitive to the age. So these are ages from 7 to 17 billion years. And if we compared them to the distances that had been measured with Cepheids or another kind of variable called an Aurora Lyrae, the agreement was really excellent. And the other advantage, and I'll go through these again quickly, I'm happy to answer questions at the end, is these are metal poor clusters shown on the left here, metal rich clusters on the right. They're actual spectroscopic abundances that have been measured. This is the magnesium line for the metal poor clusters, and you can see how much deeper it is for the metal rich clusters. But again, the position of the luminosity of the tip is really rather insensitive to the metal abundance. And we can determine that empirically in a way that, in fact, we can't do for the Cepheid variables. There's no way of doing that. This is this coefficient gamma that I mentioned. It's very difficult to determine because of a degeneracy with the temperature of the star. Now, when we go to measure the Cepheids, as I previously alluded to, these stars are young. So we find them in the disk. This is a negative image, so you can see some dust lanes here. They're white, and they're in regions of star formation, dust, gas, and so on. And we have no choice. That's where they are. In the case of the halo giants, we can go out away from the disk, and you can see the contrast here. It looks like there are no stars at all relative to the brightness of the disk. But when we use Space Telescope and measure the giants out in the halo here, you can see the well-defined giant branch, some asymptotic giant branch stars, and again, the position sample of galaxies using the Hubble that were out in the halo, a minor axis along the minor axis of the galaxy, and where we could accurately measure these tip of the red giant branch stars. This is a galaxy at 11 megaparsecs, and here's the halo field, and shown in circles are individual tip of the red giant branch stars. So they aren't blended or crowded with nearby stars, the problem that we have in the disk when we're measuring the Cepheids. Now, if we compare the distances that are measured using the Cepheids and tip of the red giant branch, they agree very well, particularly for the nearest galaxies where the scatter is low. So the points here on the red, I've expanded in the plot on the right, and the red points are there for galaxies that have Cepheids, tip of the red giant branch, and type Ia supernovae. And you can see here's the scatter for the whole sample, the nearby sample. The scatter goes up, as you would expect for more distant galaxies. The measurements are more difficult, but also chi-squared is large. That is, the scatter is larger than expected from the quoted uncertainties for the measurements. And so that's something that we still need to understand. There's an offset also in the 0 point between the Cepheid and the tip of the red giant branch distances. And that's important, of course, because if we're seeing a difference locally, we can't then say that there is a difference between the early universe and the nearby universe until we resolve the nearby distance discrepancy. I just mentioned that there's another group that has measured the tip of the red giant branch distances. These are the same galaxies, but using different techniques to measure the luminosities, to measure the position of the helium flash, and so on. But the different groups get very similar results, and if you use the same calibrating galaxy, this NGC 4258. So it's an external test that these results are repeatable and at a very high level. The mean agrees to better than 1%. Now, for the type Ia supernovae, I'll just say a few words about how we measured the supernovae. We obtained the data at Las Campanas in Chile using a wide range of telescope sizes, depending on the luminosities of the supernovae being observed. This is a project that Mark Phillips and I undertook a couple of decades ago. We began it. And the idea was to assemble a set of supernovae where we could once again deal with systematics, with well-observed supernovae. You can see we catch them before maximum, follow them through their light curves, and we obtain 9 different bands from the ultraviolet through to the near infrared to allow us to correct for the effects of dust and abundance and environment and so on. So they're very well sampled. We also got very well sampled spectroscopy as a function of phase of the supernova, which because there are these big absorption lines, we have to make what are called K corrections to allow for the shifting of bands with redshift. Also tricky and needs to be done with care. And so it really is the best, I think, self-consistent data set for dealing with systematics in the supernova distance scale. These data then for the light curves serve as input to a Markov chain Monte Carlo analysis, and that allows us to put together a Hubble diagram. Here are the more distant supernovae, part of the Carnegie Supernova Project, and the red points here are the calibrators based on this tip of the red giant branch. And that yields a value of the Hubble constant then of just shy of 70 kilometers per second per megaparsec. So this was based on our Hubble Space Telescope sample that I showed you just a moment ago. And I'll mention, so the result that we published both in 2019 and 2020 was based on this distance to the Large Magellanic Cloud as the anchor galaxy, as we had used for Cepheids. But we spent the last couple of years obtaining more data to test the 0 point that came from the Large Magellanic Cloud. So let me just briefly tell you a little bit about the tests that we've done. The first was with globular clusters in the Milky Way galaxy with a range of metallicities that bracket the range that we see in the halos of the galaxies that we're measuring. And we put together a composite HR diagram for all the clusters and use the horizontal branch to bring them to the same level. So the tip of the red giant branch stars don't know anything about where the fit is being done in the horizontal branch, but then we can measure using this composite the position of the tip of the red giant branch. And that agreed with what we found in 2019, 2020 to 1% accuracy. We then went to this maser galaxy, NGC 4258. There are data in the Hubble archive for 15 fields from Hubble that allow us to make measurements in the halo of the galaxy. The other group has been measuring in the disk of the galaxy, but as I mentioned, that's where you have the largest systematics due to presence of other stars and dust and gas and so on. So I think you really want to avoid these regions where the systematics are problematic. And when we've done this measurement in the halo, we once again get a result that is in extremely good agreement with the value that we got for the Large Magellanic Cloud. And then there's been another recent measurement that is, again, in the disk. This one's out of the disk, but the results have been combined, so we don't see the reason for the difference. We aren't able to see exactly where the difference is coming, but it's concerning because it's 2.6% in distance. And this is for one of the anchor galaxies that is one of the nearest galaxies in the sample that calibrates the type Ia supernovae. So if we're seeing, so these galaxies, this is one galaxy, it's at one distance. This is clearly a systematic effect. It's not new physics in the early universe. So it's something we need to understand. And next month, we already have scheduled deep observations in the halo of the galaxy at multi-wavelengths so that we can really ascertain, get to the bottom of where this discrepancy is. So we should be able to resolve that very soon. And we've also obtained new measurements of the tip in both the Large Magellanic Cloud and the Small Magellanic Cloud. And you can see again how exquisitely well measured the position of the tip is, again, giving in extremely good agreement with what we found earlier. The Gaia results, this is the parallax satellite. I'm just going to quickly say that we need to be cautious at this point, as the people who are part of the Gaia group have pointed out. There is both a systematic offset to the parallaxes and it's a minimum systematic error floor. And in terms of the calibration, there's now a 5% uncertainty. And the corrections for the bright stars, which are saturated still in Gaia, are even more uncertain. And that's a problem for the Cepheids, not just the tip of the red giant branch stars. So we will have to wait for the data release 4 and 5 from this satellite before we can achieve a 1% precision for them. Putting all of the data together then for these 4 independent calibrations of the tip of the red giant branch, and this I've done in several different ways. One is a frequentist and the other a Bayesian analysis, and I get very similar results. The uncertainties are larger for the frequentist errors, and at this point I've adopted the larger uncertainties, and I'll just point out that the Milky Way calibration is still at this 5% uncertainty. It doesn't have much weight. But in any case, the final result is a value, again, just under 70 kilometers per second per megaparsec. And that's a paper that just came out a couple months ago now in the Astrophysical Journal. So if we compare only the results from the cosmic microwave background, 67.4, and the tip of the red giant branch now, we would say there is no significant tension. It's 1.3 sigma. And that is interesting. And I think we need to resolve, if we had done this measurement first, that is, this key project had come before the Cepheids, I think we would probably be asking, okay, what are the systematic errors in the Cepheids? Here is a comparison now of the values of the Hubble constant based on many methods. So Planck again, the dark energy survey plus baryon acoustic oscillations and Big Bang nucleosynthesis are giving low values. Here's the tip of the red giant branch. Here are the Cepheids. And these other methods, simply plotting, these are the relative probability density distributions. And these are the published error bars for these techniques given in those analyses. And so you can see they're not yet at the level of the tip of the red giant branch or Cepheids, either in terms of statistical precision, the sample sizes, or the constraints yet on systematic errors. And some of the methods, for example, type 2 supernovae, the surface brightness fluctuations, and are based on the Cepheid calibration. So if the Cepheids have systematic error, then those will move in lockstep with the Cepheid calibration. So clearly, these are the kinds of issues that we now need to resolve. And what I'm encouraged about, and I'm very optimistic about it, is what is coming in the very near future. The Gaia measurements with a longer baseline for Gaia will get us a 0 point to the 1% level that is not possible at the current time. This calibration issue with the Maser galaxy NGC 4258, as I mentioned, we'll have Hubble observations in a month that will allow us, they're very deep, very high signal noise, multi-wavelength, allow us to resolve that discrepancy. And the James Webb Space Telescope, which is what I'm getting very excited about, is we were awarded time to measure the distances to the same galaxies using Cepheids and tip of the red giant branch, and another method using carbon stars, which is proving to be very interesting from what we've done so far. But because so the resolution of the camera that we will have NearCam with JWST is 4 times that is available now in the infrared on Hubble. If there are crowding and blending issues, we'll be able to directly see those and eliminate the stars that have been crowded and blended. We have been awarded time with a filter that allows us to measure a CO bandhead, a direct test of the metallicity for Cepheids that has not been done for this kind of study before. And in addition, we have more wavelength coverage so that we'll have better measurements of the reddenings of the Cepheids. Same in terms of the tip of the red giant branch. This increased resolution will also allow us to go out to farther distances so that we will get more galaxies and obtain better photometry, higher sensitivity, higher signal to noise photometry. So we are looking forward to that. And I'll just conclude by saying that it was really only a few decades ago that we didn't know the distances to even nearby galaxies to better than a factor of 2. But if we now include systematics, we already now have accuracies of about 2% for the nearest galaxies, the local distance scale. So we compare the tip of the red giant branch and the Cepheids for the nearby objects. As we go out to the Hubble galaxies, where we can measure the distances, we're agreeing at the 3% level. And by the time we step out to the type 1a supernovae more distant, the agreement is at a 5% level. So that's an enormous precision, a jump in precision and accuracy from where we were only a few decades ago. Gaia, as I said, is going to improve the parallax calibration in a few years. And so I think it's going to take a few more years as we get the Gaia data and JWST and further HST observations. And I think longer term, with other techniques that have systematics that are completely independent of the local distance scale, as I've described, for example, the neutron star binaries and measurements with gravitational waves. And so I think we will be able shortly to discriminate between new physics and systematic errors. We aren't there yet, but it's entirely feasible. So I'm going to stop there, and I'm very happy to answer any questions. Thank you.
Thank you so much for this very exciting talk. Very exciting. That was great.
Thank you.
So please send us questions through through message and chat button. Wendy, what is the present state of debates on these issues in sense of alternative and so on?
In terms of
at the beginning, it was hard, I can say, but at present time, I think many people think that new physics may indeed emerge here. Is it okay? What is the present status of this?
Yeah, in my view, I think it's an open question.
Still
right
very
now,
open.
Certainly the tip of the red iron. Yeah, so and I didn't, but I did allude to the fact that with Cepheids have, in particular, if in the inner parts of galaxies, as you go into the center of a galaxy, the amount of dust goes up, the amount of metals go up, the crowding and blending effects go up, and those are measure the wrong luminosity because your star has been crowded, the abundance effect wrong, and you get the reddening wrong. And so I think until we've gotten to the bottom of that, that we simply can't just assume that this is going to be resolved with new physics. Having said that, we don't know where the systematics are going to lie, right? I think we're going to get a very good picture when we have both measurements, TRGB and Cepheids with James Webb, same galaxies. And then, of course, the issue of the 0 point, the anchor galaxies with Gaia for the Milky Way and resolving it for NGC 4258. So these kinds of things that are at the 2 to 3% level and perhaps larger in the more distant galaxies, we don't know which way that's going to go. And so I really do remain open on this question. I don't know where it's going to resolve. I think it would be much more exciting to have it be new physics, but we really need to be sure that what we're measuring is a real effect and that we're not having the same kinds of systematic errors that we have made it so difficult in the past. And part of the issue is that we really don't necessarily even know what all the systematics are. There could be unknowns that are affecting these measurements. And how do you tell? You make measurements using very different kinds of techniques, which is why we're doing this in different ways. And so the first test that we have of the Cepheids, they're agreeing at the 2 sigma level. There's good agreement, but they agree somewhat better with the microwave background, and then you wouldn't have any need for new physics. So I think it really will take a few more years before we can be clear on this. And so in my view, it's an open question, completely open, in fact.
Mm-hmm. Thank you. Thank you. More question, please.
Looks like chat.
So we have one question in chat. Well, can you read, or shall I read for you?
I can see one here. So and
yes,
then
please.
Looks like also someone's raised their hand, but so I'll read the one in the chat. It says, "Well, distances of standard candles increase, their errors increase. Is that correct? How are we sure that the Hubble constant is constant?" So yes, you're correct. The errors increase with distance. The measurements get harder and harder. The luminosities of these stars, they become fainter, their apparent luminosities with distance, and the errors increase. In fact, the Hubble constant does change. I think the nomenclature, we talk about the Hubble constant, but there's a Hubble parameter which does change as a function of time or distance. And that, in fact, is what we see when we look back in the early universe. That's where the evidence for acceleration comes from, because the Hubble parameter is changing with time. And what we mean by the Hubble constant is that when we make the measurements locally at the current time, so the Hubble constant, or H0, is the Hubble constant at time equals 0. And the constant refers to the fact that if we make the measurement here, or we go to another nearby galaxy, M81, and we make the same measurements, we will see the same effect, that galaxies at larger distances are moving with faster velocities. And that's a consequence of the uniform expansion. But the constant means constant in space. We would measure the same value. But as we do look back in the early universe, we see the effects of evolution, and we have to take into account the matter density and the dark energy density. And where we make these measurements, it's an insignificant effect. We include it, but it's way less than 1%, taking into account the effects of the cosmology.
Thank you. More question, please.
Somebody had raised. They say they raised their hand, and I don't see. I don't know who that. Ibrahim Samiz. I'm probably saying it wrong, and I apologize.
Yes, that's me.
Yeah. Did you have a question?
Yeah, something ask. Yes, Ibrahim,
yes,
please.
I finally was able to unmute myself.
Okay, please.
Okay. I got 4 questions actually, but I don't want to ask them all at once, so I will allow for others as well. The first one is the central value of H0 according to Planck seems to have come down abruptly in around 2013. Is there a reason for that?
Please ask all your questions first.
Then I will get a pen because, can I find a pen? I'm sorry, 1 second. I just don't want to lose
Ibrahim,
track.
we have no time. Please ask your question.
Okay, that's my first question then. The second is that in 5-6 years ago, I've seen several papers that mentioned that there might be two distinct kinds of type 1a supernovae. Just like the case with Cepheids in 30s, and that might change some things. Have you heard anything, any developments on that end? That was my second question. The third question is that when you when you started talking about the TRGBs, you mentioned that their ages are between 7 and 17 billion years ago. Was that kind of a slip, or I mean, the universe is supposed to be 13.6 or 13.7 years old, so how can a star be 17 billion years old? And the fourth question is that in your graph comparing the different methods and their errors for H0, you do not mention type 1a supernovae. Is that because they are calibrated from Cepheids so that it is kind of included in the Cepheids?
Yeah, quick answer to your last question. Yes,
Thank
that
you.
is the case. They're calibrated with respect to the Cepheids, but the supernovae are in them, and the uncertainties of the supernovae are included in the overall uncertainty in the Hubble constant. So I guess going backwards, your third question about the supernovae, or maybe that was your second, the different kinds of supernovae. There's a hint that the luminosities of supernovae have a dependence on the mass of the galaxy in which the supernova goes off. And so it might be slightly different in spirals and elliptical galaxies, for example. So people now are arguing about the strength of the dependence of the luminosity of the supernova on the mass of the galaxy. And different samples yield slightly different results and about how strong that dependence is. And of course, it's not no one would imagine that it's the galaxy itself that determines it. They're more likely local physics, something to do with the local physics of the supernova itself within those galaxies. But in any case, the effect is relatively small. So it's not going to explain the 8% difference between 67 and 74, and the types of differences that people are talking about are at the 1 to 2% level. But that's something that will improve with time as the samples get bigger and you compare essentially exactly the same objects nearby with exactly the same kind of object more distant. So you make sure that you're looking at the same types of galaxies, for example, an elliptical comparison, or spiral and spiral comparison. That's one of the difficulties with the Cepheids, is you only find them in spirals. So it's another advantage of the tip of the red giant branch method, that you can find giants in the halos of elliptical galaxies as well as spirals, so that we can do that and test using similar objects in that case. The question about the isochrones, the 7 to 17 billion year age, that was, you notice, was published in 1990, and that was when people were still considering that the ages, we hadn't resolved the age debate. That was one of the problems with a higher value of the Hubble constant at that time, which gave a lower age, and the ages of globular clusters in the Milky Way, in some cases, were being considered to be about 16 billion years old. And that got resolved with the discovery of dark energy, and allowed you to have an older age for the universe, because the universe has been expanding in the intervening time. But the isochrones that I showed were done, those so-called Yale isochrones that had been run for that, that age range. But no, we no longer think that there are stars in the Milky Way that old. But it just was an indication that there's not a large age dependence in the models. These stars have pretty constant luminosity independent of age. And my internet went out on your first one, so I never caught the first question, if you want to repeat that. You're muted. I don't know if you want to repeat your first question.
Yes. I am unable to. The host has to first enable me to unmute myself, so he did now. Okay, the first question was the central value of H0 seems to come down pretty abruptly. From Planck data. It seems to come down pretty abruptly in around 2013. Is there a reason for that?
Yeah, so that went from the WMAP results to the Planck results. That's where that jump occurred. And Planck has 9 frequencies. It has a better angular resolution. And as you saw, the error bars also dropped. So yeah, that jump occurred when the difference between the 2 satellites.
Okay, thank you. More question, please.
But why should the 2 satellites give so drastic? Significantly different results?
Well, they do agree to within the uncertainties, and so WMAP was not able to go to as small angular scale, so larger multiple values. They just didn't have the coverage that Planck did, and so Planck has many more of the acoustic oscillation peaks measured. There are now 7 to 9 of those measured, and WMAP had fewer. So it was an improvement in the measurements, more frequencies, better angular resolution. But as you saw, the error bars did overlap. They still agree well to within the given uncertainties.
Okay. Thank you so much. More question, please. Thanks a lot for your talk. So if there are no questions, perhaps we can one question in charge. Please, last question. We can take last question. What are the possible new observation techniques? Thank you very much. So
Well, one of the ones that we're working on right now, I briefly mentioned the carbon stars, and these are looking very promising. These are stars that we identify in the near infrared. It was a technique that was first used a couple of decades ago by Nikolaev and Weinberg. And they were observing stars in the Large Magellanic Cloud and noticed that they're for a very narrow range, essentially in color, in J minus K color, the luminosity of the stars in the J band was very small. And it was small, they could actually use it to measure the geometrical tilt of the Large Magellanic Cloud. And I using data that have been published in the near infrared for nearby galaxies and measuring these carbon stars and comparing those distances with the tip of the red giant branch. And they're agreeing to a few percent. And so our James Webb Space Telescope proposal, were again, the same galaxies. So for no cost to the proposal, we can do this technique in addition. And so there'll be 3 independent measurements, the Cepheids, the tip of the red giant branch, and these carbon stars. And we'll see how well it does. But looking at ground-based data and also Hubble Space Telescope data, the more galaxies we add to the sample, the more we're becoming convinced that this is looking like a very promising method. I also mentioned the gravitational wave sirens, and I think the hope was that because the neutron star binary, the 170817 object, came so soon after LIGO turned on, that the frequency of those objects would be higher, but there hasn't been another one since. But ultimately there will be more, and what I like about that technique is that it's completely independent of the kinds of calibration issues and dealing with dust and the kinds of techniques that we use locally with the Cepheids and tip of the red giant branch and carbon stars. So if we're going to resolve this issue unambiguously, we need to have completely independent techniques, as I described for the key project, so that ultimately we have a robust estimate of the overall uncertainty. And we'll never get that with just one technique. So we can't simply rely on the, I know and love Cepheids well, but as you probably can tell, I still would like to ascertain whether or not there are remaining systematics before we would conclude unambiguously that there is new physics.
Okay, thank you. Thank you so much, Wendy, for this very nice, very great talk. So I hope that in COVID-free world, we will in person discuss all these exciting things with new issues, and we will be happy to receive you here in our institute, in our summer schools, or just visiting scientists. And that will be a great pleasure for us. Will you please give your final remarks if you would like?
Oh, I would just like to say thank you again for the invitation. And at some point, I would very much like to visit with you, and I hope we can make that happen in the future. So thanks very much.
Thank you so much. So if you don't mind, we can close our session here. Thank you very, very much. So that was great and